So in this part we are going to learn about the TensorFlow, which is the framework around machine learning algorithms provided by Google. So the advantage of TensorFlow will review over the conventional algorithm implementation that we did. So let's once again review what we did uh, last time for the linear regression implementation. So this is the NumPy implementation that is open. We generate the data. This is our toy data that we are playing with for the linear regression, and then we proceed over to generate the model to define the model. So these are the number of sample calculation, and then we have this y prediction that is our hypothesis definition, and then we calculate the error, and then we use the gradient descent to calculate the values of theta 0 and theta 1 as close as possible to our God equation. So notice that you had to do the derivation of the theta 0 theta 1 manually. So as and when our algorithm develops, so this is linear regression algorithm, right? So we'll go over few more algorithms in future. For each and every algorithm, it might be cumbersome to calculate the values of parameters, the derivation in gradient descent. So what this TensorFlow does is TensorFlow gives you a tool in which you can it's a very high level API like tf.train.gradient descent, uh, which you can use to auto calculate all these derivations, right? So that is the additional benefit that TensorFlow gives. So it's one of the framework. There are several other frameworks, PyTorch, Cafe, Theano, uh, several of them. So feel free to review. Here we'll go over the TensorFlow framework. It's most widely used. Um, let's start with that. So we'll start by importing TensorFlow. So if you don't have TensorFlow installed, please install it using either you can do pip install, or you can go to settings, go to the Python project interpreter, and using this plus search for TensorFlow. So you will see the TensorFlow, install the package, and you will have the TensorFlow install. You will require Python 3.6 or plus. So let's start with importing TensorFlow. Import TensorFlow as TF, and then let's copy over some of the parameters from our previous example. So let's call this train. Since we are training on it, let's now call this train. So we'll also require the NumPy module. So we'll import NumPy as np. So we have the data. Let's copy over the hyperparameters. Okay, so once we have the data, let's proceed over to define a model. So notice that x and y are input features and labels to the model. In TensorFlow, they can be represented using something called placeholder. So let's define that. So the placeholder for our model will be tf dot placeholder. You can define the so data type would be equal to tf.float32, and size would be equal to we'll go over the size later on. Sorry. Uh, so again, y equal to tf dot placeholder. Now it's time to define our parameters. So the parameters in TensorFlow are represented as variables. They are called variables, and variables are trainable. So this would be tf dot variable, and we use the ran, uh, random normal. So again, shape, we'll go over the shape afterwards to explain you what that means. So shape, and then I think that is it. We don't require anything else. Then we have theta1 equal to tf dot variable. Again, we'll go over the shape later on. Now next step would be defining the model, right? So let's proceed to define the model. So the input to the models for now would be x, theta 0 and theta 1. So now we'll proceed to define our hypothesis. So it's ypred equal to tf dot matmul. So what this matmul means is it's the short form for matrix multiplication. So something you need to know for matrix multiplication is the dimensions. So let's say you have m cross n matrix, and then you multiply it by n cross, let's say n cross v. The resultant matrix would be of the shape m cross v. So notice that the dimension of a row and column of the head of the matrices A and B in matmul A comma B are the same, and which will result into row of the first matrix and the column of the second matrix. Okay, so that is something that needs to be kept in mind. So we'll have theta 1 comma x. So let's say the shape of x is equal to, so the shape of x would be equal to 1 comma number of samples, right? So and so what should be the shape of theta 1? It should be equal to 1 cross 1, right? So similarly, shape of theta 0 would be equal to 1 comma 1. So since we are adding theta 1 theta 0 to each and every item in X, I think so it can be easily broadcasted. So let's keep it 1 comma 1 uh, 1 comma 1, so that it's a singular value that is added all across the board. So have theta 1, so you will do theta 0 and you will add it to our equation of y pred. And then you return this y pred. So let me explain this once again. So define a linear regression model. You take in x, theta 0 and theta 1 as an input, you define the hypothesis function and return the hypothesis function, right? So compare that to our NumPy implementation. So we did the similar thing over there. We defined the model, we defined the hypothesis, we proceeded to define the error function, and then calculate the gradient descent over the algorithm. We are going to separate this step in TensorFlow implementation, and you will know why. So let's get the data right now. X train comma y train equal to get data. So now it's time to look at the shapes of the x and y that are getting generated. So let's print x train dot shape. So let's see what is the output we get. So we'll go run. So it's 6 comma this weird looking dimension. It's because we have defined an array. Where is x? So it's because we have defined an array which starts from 2 and stops at 19 and steps of 3. So it's a single dimension array with 6 elements, and that's the reason it's showing up as 6 comma or none value. Similarly, if you plot down the value of if you do the shape, print out the value of y, I think it should be similar, right? So we have 6 training samples and 6 label samples. So of course both of them should be of same value. So first thing we need to do is we need to reshape x in this format, right? In fact, you need to reshape y as well in that format, right? Because the resultant y pred would be also in the format of 1 comma and cross sample. So if you look at 1 comma 1, the matval of theta 1 comma x would be 1 comma 1 multiplied by 1 comma and sample. So the resultant output would be 1 comma 1 cross and underscore samples, right? So and then you add theta 0 to that, which still gives us y pred as y pred of the shape 1 comma and samples, right? So we need to reshape x train equal to x train dot reshape. So this is something new kind of representation. If you write down 1 comma minus 1, what that means is there should be the dimension of x train should be 1 comma this minus 1 represents whatever the size of original x train was. So it represents the flexibility uh, that x train can assume, right? So let's say we had 10 elements, so the size of x train would be now 1 comma 10. In our case it was 6 elements. So let's print out x train and see what the shape is. So as you can see, it assumed the shape of 1 comma 6. I can print out the x train itself. And then see what difference did it make after reshaping, just to give you an idea of how it will look. So as you can see, this was with 6,1. Notice the single dimension. This is of the shape 1,6. So 1 row, 6 columns. Uh, Notice the two brackets. Now so the next step would be to also have Y train in the similar shape. Right, so just to verify we have the right shape, let's print out Y train as well. So you can notice 1,6 for the Y train as well. Right, so there you have that. So now since we have the data, let's proceed to get our ypred model equal to linear regression model x train comma theta 0 comma theta 1. Right, so there you have it. Let's also store number of samples. Let's also have the number of samples. So that would be x train dot. You can use either x train or y train, doesn't matter. So dot shape, and since we reshaped it, it would be 1. So this is the tuple which gets returned by this x train dot shape, and we want the second value of this, so that is the first index. So now we have the ypred. Now it's time to define the cost function. So with this framework, it's very easy to have the cost function. So but let's for now use define it by ourselves. So let's square, it would be ypred minus y, and then what we do is we divide by number of samples, right? So which is similar to, so as you can see, the cost function over here was we square the error and then we divide by 2n, right? So uh, divide by 2 times number of samples. So we have the cost function now. So what would be the next step? The next step would be gradient descent, right? So what we define here is optimizer equal to tf dot train dot gradient descent optimizer learning rate equal to learning rate dot optimize or dot minimize cost. So I'll explain what I did over here is, so in contrast to our numpy implementation, notice that we get the cost function, and then we proceed to do the gradient descent over time, right? So we had calculated the formula over here for theta 0 theta 1 uh, for the gradient descent. Instead in TensorFlow, this is just the high level API that we define. We give the learning rate for that descent algorithm, and then we decide we denote what we want to minimize in through that gradient descent. So cost is the thing that we wanted to minimize, right? So that's what we want to minimize. So now that we have our model defined and our input and output initialized, output input and output also defined to our model. This model is called graph in uh, TensorFlow. It's So this X train and Y train are tensors, right? So the tensors flow through that graphs, hence the name TensorFlow. So with TensorFlow, you need to do something called uh, init equal to tf dot global variable initializer. What this will do is it will initialize the variables. Uh, uh, so since now we have the graph defined, model defined, the next step would be to run this graph as a session. So with tf dot session as sesh, so we are defining the session scope. We're calling that session as ses. So you can do that with tf dot session as ses. Um, Now we do ses dot run. So we run this initialization that we did. The next step, what we do is we uh, since we have this initialized, next step would be to have cost equal to, so we want the cost for e each iteration, right? So for each iteration of gradient descent, right? So we missed writing for epoch in range 1 comma num epochs, right? So for each iteration, we see what would be the cost for this. So we do tf dot sorry, ses dot run, and we do optimizer. So we want to run the optimizer with this. So let's not return anything for now. Uh, so optimizer, and then what it needs is the feed dictionary. So what this feed dictionary is, we have the placeholders defined to our model, right? So nowhere in the model definition we are providing the input data, right? So we haven't provided any X train Y train to the model yet. So this is where we will pass our input. So this is a dictionary, so it would be Y train, right? So we have that, and for every 100th epoch we want to print out the cost function, or epoch equal to 1, right? So cost equal to sesh dot run cost comma. So this particular line over here, it would while the graph is running, it would spit out the optimizer value, which we don't need. We instead want the cost function. So every 100th epoch, uh, we run the graph on cost function and spit out the cost function, right? So we'll pass in the feed dictionary, same feed dictionary over here. So once we have that, we'll want to print uh, epoch equal to cost equal to, let's print the last four uh, precision values. So So this representation is for floating point number with 4 values after the decimal point, 4 digits after the decimal point. We'll have epoch, comma, cost. Right, so let's run this and see. Hopefully, oh, what is there? Let's made some mistake in the brackets. Right. So you have the cost function. Oh, one thing we missed was doing the sum over the cost function, right? So think reduce sum. I think reduce sum is the API for doing the sum over the whole cost function. So that's what our formula was while calculating the error over here, right? So for the cost function, right? So we missed that, and I think it printed out only one epoch. It's because our number of epochs is 100. So let's increase it to 1000 and see. As you can see, our cost function is the cost is decreasing gradually, and that's what we want. So our God equation was phi into x plus c. So our m was phi, c was 1.5. So theta 1 should be close to 5 and theta 0 should be close to 1.5. Let's observe that as well. So if you want to observe multiple values in the SAS.run, instead of just passing the cost, you also passing theta 0 and theta 1 as a list, and it will spit out those values, and you can capture that theta 0, theta 1. So theta 0 equal to, let's print them out, theta 1 equal to theta 0 and theta 1. Let's run this again and see. So as you can see, our theta 0 is approaching close to 1.5 and theta 1 is very close to 5. So you can play with the different hyperparameters over here and see what the changes, what accuracy do you get with this model. So as you can see, this framework gives you very high level APIs for quick turnaround time. You can just need to uh, you just need to call out the optimizer function over here, and as and when we go over future our algorithms, you will know there are several uh, optimizers similar to gradient descent. One of the most common one used is the Adam optimizer. It's the uh, extended version of gradient descents, improved version of gradient descents. You can learn more about this Adam optimizer online, but for now we'll stick with this gradient optimizer in this algorithm. Let's change this to 10,000 and see what is the value that we get. Right, so as you can see, it has reach very close to this 1.499, and after several epochs the cost remained constant. So you can look at the epoch like 50 around 5000, it started to become flat. uh, so you know that the uh, gradient descent algorithm has reached the local minima in our case at 5000 epoch, and you can stop the training period at that time, right? So that was TensorFlow algorithm, the linear regression algorithm in TensorFlow. Thank you very much.